Okay, the idea of optimization problem is we first set up our goal function. Okay, read the problem carefully, understand the problem such that we can write plot a graph or something, and then put all the conditions in the graph, and then try to set up the goal functions that we want to maximize or minimize. Then we will try to use the closed interval method, try to find the maximum or the minimum. And then we're done with the optimization. Okay. So this, let's continue to do some more examples. Okay, let's see this example. Distance problem. Find the closed distance. Example. Oops. Oops. Let's see this one. Maybe this one. Okay, this example. Suppose we have a parabola. Find the point on the parabola such as, okay, such that we have the closed distance. Find the point on the parabola. The equation is given by y squared is 2x. That is close to the point. To the point 1, 4. Okay, first we understand the problem, the close distance, the short distance problem. Now first we plot the graph of the parabola y squared is 2x. Okay, so you can plot the graph. You can sketch some points on this graph. When x is 2, y is 2. Okay, 1, 2, 3, 4. When x is 2, y is 1, 2. Okay, when x is 2, y is 2. When x is 1, then 1 is square root plus minus square root 2 around 1.4, negative 1.4, with this one, negative 2. So this is around here, this is around here. When x is 0, y is 0. So if you plot, it's a quadratic. Okay, so more or less like that. Okay, now the distance, now the point 1, 4, 1, 4. What's the point of 1, 4? X is 1, y is 4. Okay, so it's a, let me enter some, okay. Oh, this is not, okay. 3, 4, 1, 4 is here. Okay, so P is a 1, 4. P, 1, 4. Okay. Now the close distance. Okay, now you see from this picture, it looks like from the picture. Now it's clear that we should have some point on the parabola that is close, the shortest distance to the point P. Suppose this is the point looks like somewhere around 2. Looks like around 2. You know, suppose it's here. Suppose it's here. Okay, we just do a rough graph. So this is x and y. Okay, q, x, y. Then we find the distance PQ. So we need to minimize the distance PQ, okay, distance PQ. So if we know the coordinates of 2 points, then we can use distance formula so to find the distance PQ, okay, by the distance formula. Okay, by the distance formula. Distance formula. PQ squared, okay, PQ squared. We know the coordinate of P and Q, so you can find PQ squared. PQ squared by Pythagorean theorem, then x minus x, x minus x coordinate of Q is x minus x coordinate of P, x minus y squared, plus y minus the y coordinate of P, which is 4, okay? Okay, so we want to minimize PQ. It suffices to minimize the square of a PQ, okay? Okay, so we want to minimize PQ, so it suffices to minimize PQ squared. Now here the right side has 2 variables, okay, variable x and variable y. Now it's hard to manipulate the 2 variable functions. So what we do here is we will try to simplify x, substitute x in terms of a function of a y, okay? Remember, since we have a relation between x and y, you know, note that Q is on the curve. Q is on the curve, on the parabola. Y squared is 2x. Then we actually know this implies, so we can substitute. So this means x and y of coordinate of Q satisfies the relation, okay? Y squared is 2x. So we can solve x. Now, if you solve y, it's also okay, but here it's unpleasant to solve y because you need to take a square root. Okay, so here we solve x. We replace x in terms of a function of y. So this implies x, which is 1/2 of y squared. Okay, then what we do is, so this implies PQ squared is 1/2 of y squared minus y squared plus y minus 4 squared. I think we try to simplify this, okay? Expand the bracket by perfect square formula. So this actually gives us 1/2 y squared minus 2 times 1/2 y squared plus times negative y plus y squared. Y minus 4 squared, then we do the plus y squared minus 2 times 4 times y plus negative 4 squared. Okay, so this we get a quarter y squared, so y power 4. And then what do we get for y squared? Now y squared, what we get is, now we get the term negative y squared. This term we combine similar terms, okay, combine similar terms. Now this we get y squared, you see the y squared coefficient is 0 actually. Y squared coefficient negative 1 plus y. So get y squared coefficient is 0. So this term is gone. And then the term negative, the term that degree 1. So get negative 8y, negative 8y. Then the constant term 1 plus 16, so plus 17. Okay, so this is a function of fy. So we define this thing to be f of y. Now, what's the range of y? What's the range of y? So y is all real number. You see, on the parabola, y can be negative, y can be positive. Look at the parabola. Y can be anything. Okay, the height of the points can be anything. It can be below the x-axis. It can be above the x-axis. It can be anything. So y is all real number. So we need to find the minimum of this function. Okay, it's not obvious that the right side is actually positive, because however, if you look at the left side, you see PQ squared is positive. So this function fy is always positive. So to find its minimum, we find its critical numbers. Okay, f derivative of y differentiate. Use power rule, a quarter y power 4, so we get a quarter times 4y cubed by power rule. Now negative 8y has derivative negative 8. 17 has derivative 0. So this is y cubed minus 8. Y cubed minus 8. Okay, so let y prime, let f prime of y be 0. So that we find creative numbers. So y cubed is 8. And then take cubic root, so we get y is actually 2. Y is 2, then x, remember y squared is 2x. This means x is y half y squared, plug in 2. Y half of 4, which is we get 2. So here you see, so which means the q. Here we only have one creative number. We only have one creative number. This means this is the unique solution for this problem. Okay, this is the unique solution of this problem. Another way to see this fy achieves the minimum at when y is 2, then actually you can do the following. Okay, so you check negative infinity to 2, and then 2 to infinity. F derivative of y and f of y. So this is the, you check it. When y is from this part, it's negative. When y from 2 to infinity greater than 2, y is greater than 2, then remember y derivative is the y cubed minus 8. Okay, if y is greater than 2, for instance, y is 3. 3 cubed is 27. 27 minus 8, which is positive. So this is actually positive when y is from 2 to infinity. F derivative of y is positive. Then by the increasing decreasing test, okay. For instance, from the interval negative infinity to 2, you plug in y to be 0. Then you see f derivative of y. Plug in y cubed minus 8. Plug in y to 0. Then you get negative 8. Okay. So f derivative is negative. So this, then we apply the increasing decreasing test. Okay. Derivative is negative, means the functions are decreasing. So we get a decreasing. Now derivative is positive, then the functions are increasing. So we can conclude that actually the functions are decreasing then increasing. Decreasing then increasing. So you see we have a local minimum. Actually it's global minimum. Global minimum. At the boundary, you know, at y equals 2, at y equals 2. Okay, so this is the minimum. Okay, you see from the picture, this is 1, 2, 3, 4. Now you see the point Q. What we plot in this rough graph, you see Q is really close to the point 2, 2. Okay, so actually this Q is actually 2, 2. This 2, 2 is the shortest point. In this case, the distance is the shortest. Now it's more or less is true from this picture what we just plotted. Okay. Now the shortest distance is, in this case we find the shortest distance. We find the shortest distance in this case. Okay, so okay, the shortest distance. What I did here. So this is a y power quarter. Okay, if you plug in that thing, so if y is 2, so y at y equals 2 and y equals 2, then fy distance squared, remember, is a quarter y power 4 minus 8y plus 17. You plug in y to be 2, okay? Plug in y to be 2. Then you find this is a quarter 2 to the power 4 minus 8 times 2 plus 17. 2 to the power 4, 16. Divided by 4, so we get 16 divided by 4, so we get a 4. Minus 16 plus 17. Okay, so this is actually negative 12 plus 17. So we get this is the 5. Now this is distance squared. So PQ minimum is, we take square root of 5. Okay, shortest distance. Okay, shortest distance. Okay. Then the conclusion that we write down is if Q at the point, okay, the point. So the conclusion is the point Q 2 on the parabola y squared equals 2x has the shortest distance. The shortest distance shortest distance in this case is square root of 5 to the point 1,4. Okay, to the point 1,4. More example. Let's see this problem. We want to maximize the area. Okay, find the area of the largest rectangle. So that it can be inscribed in a semicircle. Of radius r. Okay. Find the area of the last rectangle that inscribed in a rectangle, in a semicircle of radius r. So we plot a semicircle of radius r. So plot a semicircle of radius r. Okay, suppose we have a semicircle of radius r. This is x. This is y. Okay. Semicircle radius r. Now inscribe a rectangle. Okay, so this is a rectangle ABCD in the semicircle radius r. Okay, so here this point is r. Then we find the area of the rectangle. Now, what we do is we assume so we first find what determines the area. What determines of the area of the rectangle. Now, the area formula of a rectangle is length times width. Okay, length times width. So we need to find what determines the length and what determines the width. Okay, first we assume. So here, B, we find the coordinate of B to be x. Okay, x. This point to be x. Then the point of what is C? What's the x coordinate of C? C is x. Okay. Now what's the y coordinate of C? Suppose we just y. Okay. The height is y. Oh, this is 0. Okay. So we find area formula. Area is length times width. Area A is 2x. Okay. Length is AB. Okay. AB times BC. So length width is times y. So here we have two variables, x and y. Remember, when we have two variable functions, usually what we do is we substitute one variable so that we get a one variable function. Okay, so we need to find a relation between x and y. Okay. Now, what's the relation between x and y? Note that the point C, okay, is xy is on the circle, So the x1 cannot be arbitrary. It should be restricted on the circle. This gives a relation between x and y, okay? Now the equation of the circle. Remember equation of the circle of the given circle or semicircle. Semicircle is, now the circle is the set of points that has a fixed distance to the center. Okay, a circle is a collection of points that has fixed distance to a given point called the center. So if you write down the distance formula, then you get x squared plus y squared. This is distance. Distance squared is, the distance is radius. Radius is r. So it's x squared plus y squared is r squared. X squared plus y squared is distance to the origin O. Okay. The left side is distance square of the distance to the center O of a point xy. Okay. The right side is radius squared. Okay, here the semicircle, here we assume y is, non-negative. So this upper half of a circle. So it's a semicircle. Okay, so that we can try to solve y in terms of x. So you solve y squared, then you're gonna move the term x squared to the other side. So you get r squared minus x squared. Okay. And then you need to solve y. Remember, we need to substitute y. Now y, when we take a square root, you need to be really careful. We have a two choice, whether it's plus or minus. Okay, we have two branches. But here we only have one branch because we are, using the upper half. Okay, upper half circle. So it's a y value is positive. So we only have the positive value. So the negative value is lower half. We don't use that lower half because y is positive. Then we substitute y into the area formula. Substitute y. Substitute y into the area formula. Area formula on the first line. Then what we get is a is 2x times y, which is r squared minus x squared. Now this is we assume this thing to be ax. Then we need to find maximum of ax. Okay, so ax is the thing. So what's the range of x? Now you see here x so lies in between. We assume x can be positive by symmetry. X is positive. X is bounded by the radius r. Okay, because the rectangle is inscribed in the circle. So b cannot, the x value OB should be less than the radius. Okay, OB should be less than the radius. So x should be less than equal to r. Okay, so we find it. So we get an interval. Then we find the maximum of this area function. Then the first step, of course, is differentiate a prime x. Use differentiation. So here we have a product. Use product rule. Okay, product rule. So 2x square root r squared minus x squared. So derivative. Use product rule. Okay, product rule. Use product rule. So we get 2x derivative. So you can get 2 factor 2 times x derivative times r squared minus x squared minus x times r squared minus x squared root derivative. So we apply the power rule. We apply the product rule. So this is twice x derivative is just 1. Now x multiply. This thing we use chain rule. Okay, we use chain rule. So if you use chain rule, you get this thing multiplied by. So the inner derivative is negative 2x. Okay, inner derivative. So what we get is this twice, do some algebra. So minus minus, we get plus x squared. Did I make any mistake? No mistake. Okay. Then what we do is okay. Okay, so here, yes, it's wrong here because the reason is in the product rule we use addition. Okay, in quotient rule we use subtraction. Okay, so this subtraction. So this actually, if you use common denominator, so this use common denominator. So this is the square root of r squared minus x squared. Then square root multiply, use common denominator, square root multiply square root. Then we get r squared minus x squared. Then minus x squared. Common denominator. So we get a twice r squared minus x squared minus x squared minus twice x squared over square root r squared minus x squared. So here x cannot be r. X cannot be r because the derivative vanishes. That's the denominator problem. The denominator vanishes if x is r. So it's not differentiable when x is r. Okay, so the critical number is, find the critical number. Let e prime to be 0. So we find this thing to be 0. Twice r squared minus 2x squared over r squared minus x squared square root. The thing is 0. Then we get the numerator is actually 0. R squared minus 2x squared is 0. So we get a x squared is 1/2 r squared. So we get a x, x is plus minus, take square root. It's root 2 over 2 of r. So it suffices only take the positive part. Here, by symmetry, we only take one part. Okay, the other part we give the same solution by symmetry. Okay. Okay, actually this gives us the unique solution of this optimization problem. Now the other, if x is 0 and x equals r, the boundary value, if x equals 0 or x equals r, then it's easy to check. Ax equals 0. Ax equals 0. This is trivial case. This is very trivial case. You plug in x 0 and r, you find the area is just 0. So in this case, we don't get a rectangle. We get a line. Okay. So this only gives one solution. So A maximum is A plug in root 2 over 2 r. Then what you get is remember area formula is 2x times y. In this case, so r squared minus x squared, root 2 over 2 r squared. Okay, so 2 cancel, and then 2 cancel 2. So this is the root 2 r. This is the 1/2 r squared. Okay, 1/2 r squared. Then this you get actually finally get r squared. Okay. So the solution is the maximum area is achieved when x is root 2 over 2 of r. Okay, so the maximum area we are done with, we get r squared. Okay, in this case, x equals 1 equals root 2 over 2 r. So use actually this point is pi over 4, 45 degree. Okay, 45 degree. Okay. In this case, x and y, they are equal. So we have an isosceles right triangle. Okay. It's the angle is pi over 4. Okay. So BOC, angle BOC is pi over 4 in this case. So we get the minimum, maximum. Okay, another way we can also use trig identity. It's actually easier than the solution. that we did above. Another way we do this, use trig identity. We can also use trig identity. Okay, suppose we have a circle. We have a semicircle. It's more or less like a semicircle. Okay, so this is radius at r. Okay, so this is the angle theta. This is the ABCD, ABCD. Now the radius, OC is radius. OC is the radius of the circle. So OC is R, radius of the circle, semicircle. Okay, so because we have a rectangle, CB is perpendicular to OB. So we have a right triangle. So in the right triangle, then we can use trigonometry so that we can find OB over OC. So this is actually cosine of theta. Adjacent over hypotenuse. Okay. Now BC over OC is sine theta. Opposite over hypotenuse. Okay. So that we can solve. OC is, OB is OC times cosine theta, which is OC is radius r. So we substitute OC by r. So it's r cosine theta. Now BC is the height of the rectangle is OC times sine theta, which is OC is radius r times sine theta. Okay, so we find area is area. A is okay. So somehow A is overused. Area. So area E is so A theta is a function of theta. Okay, once theta is determined, so this unique determine the rectangle. Okay, so the area is uniquely determined by theta. So the area is a function of a theta. So theta unique determines. So theta determines the rectangle uniquely. Rectangle. Okay, determines the rectangle. So this actually theta determines area, the area of the rectangle. So area is a unique determined by theta. So A theta is AB twice OB, okay, twice OB times BC. Then you write down OB is R times cosine theta, BC is R times sine theta. So what you get is R squared times 2 sine theta times cosine theta. And then apply trig identity. So this you get R squared times sine 2 theta. Sine 2 theta. Remember, the value of sine is bounded. Sine 2 theta is bounded by above, from above. It's bounded by 1. So if sine 2 theta is actually achieve its maximum, then we know that, okay, then this is less than equal to R squared times 1, which is R squared. Okay, so if theta sine 2 theta is 1, i.e. 2 theta is pi over 2, 90 degree. This means theta is pi over 4, i.e. 45 degree. Then the area is the largest. Then the area function attains its maximum. Now its maximum is clearly R squared. Okay, R squared. Then we are done. Then we get actually the more information, the geometry, when the angle is actually pi over 4. Or we have, now if you look at this picture, when the area is achieved maximum, when the rectangle is actually has 2 squares, okay? In the first quadrant, then we get a square. In the second quadrant, then we also get a square, okay? So the rectangle is actually consists of 2 squares, okay? 2 squares. Okay, So this is the conditions when this function achieves maximum. Okay, any questions? Any questions? All right. Maybe so the optimization turns out to be really important in physics, in mathematics, in our reality. Now, maybe I mention one general idea in physics, and it's right now it's really important in current research in quantum computer, something called quantum computation. Now, in physics, let me do some digression. In physics, we have a principle called the Fermat principle. Okay, Fermat principle. Fermat principle says that if you have 2 points, A and B, then if light travels from A to B, then light always takes the shortest path. Okay, so suppose A to B. There are all possible ways from A to B. Okay, path 1, P1, path 2, P2, etc., etc., Pn, P3, etc., etc. Okay, the shortest, the Fermat principle. Principle says light travels always takes the shortest distance, the shortest path from A to B. For all possible ways, among all possible ways. So among all possible ways from A to B, Okay, now if you think about this problem, think about this principle, it turns out to be really remarkable. I.e., the principle of nature, the law of light, is governed by the optimization problem. Okay, the law of nature is governed by, the optimization problem. Actually, this is one of the most fundamental principle of physics of nature. Okay, which is called the least action principle. Now, for physicists, they want to find a function called the action of the nature. And then they try to find the minimum, okay? Try to find the minimum of the function, in which condition that the function attains its minimum. In that situation, then we derive all possible laws of nature. I.e., for instance, Newton's law. We can derive Newton's law from least action principle. Okay, so this actually what people want to construct, what the physicists want to construct is a function called the action. Okay, action of the nature. Okay, and then use optimization to derive the law of nature. Okay, another way to think about the Fermat principle is, if light travels from A to B, now how does light know actually the path that the light takes? The light take is actually the shortest distance, the shortest path. Okay, now if you travel from Philadelphia to New York, how do you know the way you take is actually the shortest? Okay, the answer is, to find the path is shortest, light have to travel all possible ways. Okay, actually it seems like light only takes one way, but however, light can actually take all the way simultaneously, so that light choose the shortest one. Okay, in this case, light actually choose all possible ways, and it only the shortest one show up. Okay, now you see, light takes all possible ways simultaneously from this idea. Now, if you design some computer, design some computation devices, then let light travel from A to B. Now you see, light travel from A to B takes all possible paths, and then if you design a thousand many paths, then light travel all paths, then you can do the computation simultaneously for this 1,000 many paths. Okay, so this actually makes global computation possible. Okay, so so here the global nature of light makes global computation. For instance, if you do a summation, do the average, sum 1,000 things together, or do the average. Now you can actually use light, because light travels simultaneously 1,000 many paths. Then you can use the global computing, do this 1,000 computation simultaneously, makes global computation possible. So this is actually the idea. This is actually the idea of quantum computation. This is actually one of the most active research area, quantum computer, because this global power, global nature of computation. Now, if you have 1,000, if you have a trading cases, a large number, okay, this can be really hard to manipulate by our classical computer because the computation is really large. However, by the global nature of the quantum computer, then actually you can compute these things simultaneously, a trading cases simultaneously. Then this makes this computation a lot easier. Then many algorithms, cryptographic algorithms of information security, use this kind of security, cryptography. Now this can beat the classical computer, such that our current information security will be challenged. So this is actually one of the reasons that quantum computer is so important. It has very important application, in information security. Okay. All right. This is the diagram of this Fermat principle and quantum computation. Okay. Any questions? No question. Okay. All right. Now we have 30 minutes. Now we start a new section called the Newton's method. The Newton's method. The Newton's method. The Newton's method. Oh, that's Newton's method. Newton's method. Newton's method. Okay. Newton's method is actually really effective way to compute the root of certain functions. Okay. This method was discovered by Sir Isaac Newton, of course, Sir Isaac Newton. Let's see one example. Okay, example. Find a root of the equation Cx, let's see this equation, x power 5 plus x, let's see, minus 1 is 0. First, now this is degree 5 equation. Now, there are some history of some math equations. Now, first of all, we know how to solve quadratic in high school algebra. Okay, there's a formula called quadratic formula. Okay, then people can solve the general quadratic formula, whether it has root or not. We know it completely. And then people try to find the solution for degree 3 and degree 4. It turns out degree 3 and degree 4, they are a similar formula, similar like the quadratic, but it's more complicated. The solution exists, okay, by radicals. You can use radicals to find the solution of the equation. Then after people find a solution for degree 3 and degree 4, people try to find a general solution for the degree 5 equation. Then two mathematicians, degree 5 equations. Okay, degree 5 equations. Degree 5 equations. Degree 5 equations. Degree 5 equations. Equations. In general, cannot be solved using only radicals. So this actually one of the milestone of mathematics. This is done by two mathematicians, Abel and Galois. They died really young. Okay, Galois died around 20 or something. Abel died at 27 or 29 or something. They died really young. This turns out to be really important contribution in mathematics. In the 21st century of the mathematics, these names, Galois and Abel, they just everywhere. Okay, now for this equation, degree 5 equation, we cannot solve it by radicals. We cannot solve it using only square root or something. Okay, square root, taking radicals. Now, how do we solve it? Actually, we can use the Newton's method to solve this problem. First of all, if you let fx be this function, fx be x power 5 plus x minus 1. First, this is continuous. Then fx is continuous. Then fx is continuous everywhere. Continuous everywhere because it's polynomial. And then you check f0, you get f0, 0 power 5 plus 0 minus 1, which is -1, less than 0. Now f1, which is 1 to the power 5 plus 1 minus 1, which is 1, okay, which is greater than 0. So we can conclude by the continuity. So when x is this is 0, this is 1. Now if you plot this graph, 0 is -1, now 1 is +1. So somehow, if by continuity, somehow there's one root x0. So we know by continuity or intermediate value theorem, continuity, okay, we know there exists a root. There exists root x0 from the point on the interval 0 to 1, actually close open interval from 0 to 1, okay, from 0 to 1. Now we find numerically thing. We compute x0 numerically. Numerically. Okay. Now we use the following idea of Newton's method. Okay, Newton's method. The idea of Newton's method is the following. Okay, suppose we have a function fx, y equal fx. Now it has a certain root when the function intersects with x-axis. Okay, now this is x0 that we want to find. Okay, This is x0 that we want to find. Okay, x0 is what we want to find numerically. Now, first of all, we have certain rough information about this x0. You know, we can use intermediate value theorem to locate this x0 roughly. You know, rough information. From the example that we did is actually we know it's bounded from 0 and 1. So you can choose a number near this x0. Okay, suppose you choose a number x0. So x1 is here, is a number near x0. Okay, choose a point. So let's use okay. What we do is x1. Then the intersect. So go upstairs from x1. Go to look at the intersection with the curve. Then at x1, we do the tangent line. Plot tangent line. So this point is x1, y1. We plot the tangent line. Plot tangent line to the given point. Okay. Then the tangent line L1 intersect at a point x2. Then x2. So the idea is pick a point x1 near the root x0. Then plot tangent line. L to the curve. Y equals fx at x1, y1. Okay. Then here y1 is of course y1 equals a function value at x1. Then the intersection. Then L, the intersection. L intersect. Suppose L intersect the x-axis at x2. Then you see, then x2 is a better approximation. It's better approximation It's closer, better approximation of x0. Okay, so x2 is even closer to our desired x0. Okay, we don't know x0, but we know x1, x2. Okay, we can pick x1. So then you see, there's no reason to stop. Then we repeat the above procedure. Okay, so now look at this graph. So we have x2 now. Start from x1. Then we plot tangent line at x1. Okay, then intersect the tangent line intersect the x-axis at x2. Then at x2 we repeat the above procedure. Okay, lift it upstairs on the curve. Okay, find the intersection. Now this is the P1. This is the P2. Now at P2 we plot tangent line again. Okay, so then you get x3. Okay, you see x3 is even closer to x0. Now again you do this thing again. At x3 you see, lift it upstairs on the curve and then plot the tangent line. Okay, plot tangent line. Then you see this is the x4. And you see x repeat above procedure. Now you know, if it get object close to x0, then this thing actually get object close to our desired root. Then what do we do? Repeat above the procedure. Then repeat the above process to find x3, x4, etc., etc. Then this gives a better and better approximation of our x0. Okay, which in general, which it may, which usually right, usually. Sometimes this method can fail if you use some very tricky example, but in most cases it's a really good method. This is which usually converges get object groups. Arbitrarily close to x0. Okay, so let's unravel the process. Now from x0, x1, we write down the tangent line equation L1. Okay, the tangent line equation at P1. So tangent line to y equals fx at x1. The y1 is y1. Y1 is f function value at x1. So we can find the equation of L1. Okay, we can find the equation of. Okay, we can find the equation. We can find the equation L1. Y minus y value fx1 equals slope. Slope is given by derivative. Remember, slope is given by derivative. The derivative is given derivative f derivative at x1, x minus x1. Okay, so this tangent line equation at P1. Now its intersection to find set to remember x2 is the intersection of L1. X2 equals L1 intersect x-axis. The intersection any point on the x-axis is y coordinate, its height is 0. Okay, so to find xy, to find x2, set y equals 0. A point has height 0 on the x-axis in the equation of L1. Okay, so we set y to be 0. So we get 0 minus, so we set y to be 0. Plug in to the equation of L1. Set y to be 0, then we get x, f derivative at x1, x minus x1. So you solve the thing. So it's negative f x1. Divided by derivative. Okay, divided by the derivative goes to the left, divide. Okay, so f derivative x, y equals x minus x1. So you find, solve for x. So move x1 to the other side. You get xy minus f x1 times f derivative at xy. Okay. So this x value is just x2. Okay. The x value gives us x2. Okay. So x2 is the thing. Repeat, then we repeat it, then we repeat it. So x3 is use the same algorithm, L2 minus f x2, f derivative f at x2. Okay, etc. Okay, etc. So this is called iteration. We use this iteration. Okay, so the general iteration is xn plus 1 is xn minus f at xn over f derivative at xn. Okay, so let's go back to our example. Go back to our example and see how this works. Now the example is fx is x power 5 plus x minus 0. Okay. Okay. So we start from it's the x0 is bounded from 0 to 1. x0. Now we choose a point near x0. Okay, we choose a point near x0. Now we know it's within 0 and 1. Now we pick any point, reasonable point within 0 and 1. So let's see, we do 1/2. Okay, now you can check 1/2 is not a root. You are not so lucky. So pick x1, a point near x0, to be 1/2. You know, for instance, we don't know x0, but we know it's within 1 and 0. Then you see, we do this thing. So let each x to be, we use this iteration x minus fx over f derivative x. Okay, now fx, what is fx? Fx is, you know, you plug in. So this is actually x minus, fx is x power 5 plus x minus 1. F derivative is use power 5x power 4 plus 1. Okay, plus 1. So then we plug in. Now it's better to use a calculator or a programming. Okay, now we use program. Okay, let's see how we use this thing. How does this thing works? Use programmer. Okay, let's see. Can everyone see the seed? Okay. Okay, so let's see. We define a variable x. Okay, then we define the function f, which is the x. Okay, let me make it I'll make it bigger. Okay, x to the power 5 plus x minus 1. Okay, so fx is the thing. Now, remember we define hx to be x minus fx over, remember, f dot derivative. Okay, so hx, so gx is f derivative. Hx is x minus fx over gx. Okay, hx. All right, so you see we start from 1/2. Okay, so x1 to be 1/2. Okay, then we do iteration. Okay, so for instance, how do we find h1 is x1? Okay, then we do, so this is the x2 is the thing. Now x3 is hx2. Now this kind of, if you do this thing, it's actually really tedious. So we use a programming. We use a loop. If you know Python, if you do how to do the loop, okay. For I in range, let's see, 1 to 10. Okay, x1 to be hxy. Okay, print I rrxy. Okay, let's do the thing. You see, this gives us, every time we repeat this step, then this gives us all possible, you know, the first input, the first output gives us, you know, x2. And then the second line gives us x3. Second line, use the Newton's method. Then you check. You see from this, you know, from 4, from 4 to 5, you know, I equal 4 and 5. You see many digits actually stabilize. You see many digits stabilize. You know, from 6 to 9, all the digits actually stabilize. So So you check, actually we get a stable solution. We get a stable solution. This is our root. This is our root. If you check f, you check x, y. Now what's the after? Okay, sorry. R, x, y. Okay. So suppose this is actually a to be the thing. Okay. Now this root is really good. Now if you plug in the function, you check. Once you plug in the function, this thing should be a 0. This thing should be a 0 of the function value. Okay, so if you plug in a, you see -8 to the power of 10 to the -17. This is a really, really small number, close to 0. This shows us that a is a really good approximation of a root of f, so that we get a a good root. Okay. Actually, this actually let's use. Okay. Now here we are. Okay. So let's copy the data to the, let's use y-half. Then we just run this thing again, so that we can save the thing to the our, so the following data. Running this algorithm. Then we get then we make it bigger. Okay, then this data that we get, you see, after several times, a few iteration. This first digit stabilize. So we get so this we can choose one checks 0.7548 blah blah blah, gives a really good approximation of is indeed a root. Now to give a good approximation is a good. Let's just assume it's a good. It is a solution. It's really good approximation of the root of f. Okay. Then we're done for this problem. Okay. Okay. One more example. Okay. Oh, sorry. Can you see the white note or not? Can everyone see the white note now? Okay. Okay, so another example. Okay, another example. Find the solution of this. Solve this. Find a root of the equation. cosine x equals x. Okay, now this thing is called transcendental. Transcendental. Here you have polynomial, you have cosine and sine. This thing is called transcendental function. Then in general, it's really hard. Transcendental function is hard to compute by hand. This is actually one of the reasons why we call it transcendental. Okay. So the function we solve this, we want to solve this cosine x minus x is 0. Okay. So we choose fx. Let fx to be cosine x minus x. Okay. So cosine 0, f0 is cosine 0 minus 0. Cosine 0 is 1, so this is 1. Positive. f1 is cosine 1 minus 1. Cosine is bounded by 1, so it's negative. Okay, this is negative. So by continuity, by IVT, intermediate value theorem, there exists a root. There exists a root. Actually, a unique root is an increasing root in 0 to 1. Okay, now we use iteration. We choose x to be 1/2, x1 to be 1/2. Use iteration. F n plus 1 equal to x minus f over f derivative. Let me quickly do this example. Okay, so this will be x minus fx is fx cosine x minus x. F derivative is negative sine x minus 1. Okay, plug in derivative. So this is actually the iteration xn. Okay, so we use the iteration. Let's use y node. Let's use this thing. Okay, so here we change our function. Our fx to be cosine x minus x. Okay, minus x. Then x1, which is x1 to be 1/2, 0.5. Then what we do iteration is, let's see, hx is x minus fx over f dot derivative. Oh, it's not. Gx is, gx equal to f dot derivative. Now hx to be x minus fx over gx. Okay, so this is h. This is the h that we want to solve. Okay, then what we do is, let's use computation. Let's use this iteration. Okay, this is exactly the iteration. Okay, you see this, after several times of iteration, the digits of our output, the xn, you see the xn actually converges to a number. It gets object close to the number. Okay, after 1, 2, 3, this algorithm converts really quickly to the solution. After 3 or 4 times, you see the digits is really good enough. No change anymore. From 4, 5, 7, 5, 6, 7, 8, 9, and no longer change. So this actually gives us a root. You can check. This thing gives us a root. So paste. This gives us the root. Okay, this gives us the root. Okay, you can easily check this. This gives us a root. Okay. All right. Okay, I think let me stop here. The time is out now. Okay, let me stop here. Next time we will do more examples of the Newton's method.